Hey everybody, Mr. Brooks here again. So we are going to be covering section 4.5 today, which is real eigenvalues and the phase plane. So in the previous section, 4.4, we learned that eigenvalues and eigenvectors are the keys to solutions of systems of linear constant coefficient first order equations. So that was a mouthful. So like in chapter 3, we'll investigate what is needed when we have real distinct eigenvalues. And then just like before, we're going to have dedicated sections. So 4.6 and 4.7 will work with complex, and then we'll also deal with repeated values as well. So the first thing that comes into play here is recognizing fundamental sets of solutions. So there's a couple of ways that we can do this. There's a really cool theorem that comes out of this one because we are dealing with matrices. So we're going to investigate that here in just a second and then get into solving these guys. And then another cool aspect or feature in this particular section is phase planes, which sound horrible, but they're actually really beneficial. So it's going to have throwbacks to section 1.3 when we dealt with direction fields, and we'll get into that at the end of this lecture too. So again, recognizing fundamental sets of solutions. If we find eigenpairs, which we talked about in the previous section, so eigenpairs are the form lambda 1 x1, where lambda 1 is your eigenvalue, x1 is your eigenvector, lambda 2 x2, all the way up to lambda sub n x sub n. How do we know if the solutions of the form y1 or y sub I of t, which is equal to e to the lambda I t x of I, form a fundamental set? Well, one thing that we could do is we could use the Wronskian to figure that out. So the Wronskian is equal to the determinant of t. So another way to say that is the determinant of, and we're going to bring this one back again, of psi for that one, where psi, and here we want the Wronskian to be non-zero, where psi is of the form y1, y2, and so forth up to y sub n. Okay, so that's our normal thing. Well, that we saw can take up quite a bit of time, especially if we get to higher or larger set of equations when we get there. So this is really the cool part when theorem 4.6 comes into play. So what it states, and that's coming out of this section, so I'm not pulling anything new here. So consider our linear homogeneous system where A is a constant matrix, okay, and we're on the interval from negative infinity to infinity. So let the constant matrix A have the eigenpairs of lambda 1, x1, all the way up to lambda sub n, x sub n, okay, where the eigenvectors are linearly independent. Okay, then the set of solutions of the form e to the lambda I or lambda 1 t x1, e to the lambda 2 t x2, so forth up to e to the lambda sub n t x of n is a fundamental set of solutions. All right, so if we could show that these eigenvectors are linearly independent, then we can automatically say that these guys form a fundamental set, which is awesome. We don't have to do any calculation with the Wronskian and we're done. That's the cool part. So here's an important note. So when A, so I'm going to put this in that red, so when A is an n by n constant matrix that possesses an n set of linearly independent eigenvectors, so that's a lot to write down, or set of n linearly independent eigenvectors, we say A has what we call a full set of eigenvectors. And we're going to talk about what a full set means here in a second. That took up less space than I thought of, so I'll put the eigenvectors down here. So again, if it has n linearly independent eigenvectors, then we can say that it has a full set. If A fails to have a set of linearly independent eigenvectors, catching myself here, I left the last part of independent off. So independent eigenvectors, we say A is defective. And we are going to explore that in section 4.7. So we're not going to talk about it now. So what we are going to do is focus on the previous. So having a full set of eigenvectors. All right. So again, we are going to cover two cases with the constant matrix A has a full set of eigenvectors. And some of this is going to be stemming off of what we found out in linear algebra. Okay, so and the nice thing is we are going to talk about what that means. So if A has n distinct eigenvalues, then A has a full set of eigenvectors. So that's the nice thing about this. So that means if we find out that it has no repeated values, so notice that's why we're reserving that for 4.6 and 4.7, and they're real, again, that's the section that we're dealing with, then we can automatically say that A has a full set of eigenvectors. There's no need to prove that part that they are linearly independent. So a note from this is this fact was proven in most linear algebra courses. So we're not going to talk about a proof, but what happens is if we have distinct eigenvalues have linearly independent eigenvectors. So that's the nice thing. We already know this. So again, if we have an indistinct number, so if we have three differential equations, then we're going to have, and we have three eigenvectors that are distinct from each other, then we already know that it has a full set of eigenvectors. Therefore, we already know that it forms a fundamental set. All right, moving on. Case number 2 is if A is a symmetric real matrix, then A has a full set of eigenvectors. Now this is going to come up in handy in our second example. So A is symmetric if A transpose is equal to A. So if you flip everything, switch we're going to alter or do a reflection really about the diagonal, but it's transposing rows with columns and columns with rows is what happens for a symmetric real matrix. So if that's the case, that's the other cool part, is if we can identify a symmetric matrix, then A has a full set of eigenvectors. So we either find all of the eigenvalues and find out that they're distinct, then we have a full set of eigenvectors, which means they're linearly independent, therefore form a fundamental set. Or if we have a symmetric real matrix, then A has a full set of eigenvectors, therefore it forms a fundamental set. So that's the cool thing, is we can automatically say it has a fundamental set without having to dive in as deep as what we have in the previous section. So to go over an example of this, let's look at this IVP here, and we are going to solve this one. So we haven't solved a lot lately, so this is going to be a good reminder of what to do for this process. So here we have y1 prime is equal to y1 minus 3y2, and its initial value is at 0, it's equal to 1, and y2 prime is equal to y1 plus 5y2, and here again 0, 1. All right, so first of all, let's write out what our matrix is. So our solution. So here A is equal to the matrix of 1, negative 3, 1, 5. Make that 5 a little bit more. And so now we need to find the eigenvalues of A. So notice here I do not have a symmetric matrix here, which is cool. That's fine. So what we need to do is recall from the previous section that A minus lambda I times our eigenvector is equal to 0. So we need to find out the determinant of A minus lambda I, which is equal to the determinant of the following matrix of 1 minus lambda, negative 3, 1, and 5 minus lambda. All right, when we cross multiply, we're going to get 1 minus lambda times 5 minus lambda minus negative 3, so plus 3. All right, when we FOIL this out, we will get 5 minus 6 lambda plus lambda squared plus 3. So now we're going to set this equal to 0 here in just a second. Lambda squared minus 6 lambda plus 8 is equal to 0. So we're going to get lambda minus 4 and lambda minus 2 is equal to 0. Therefore, we get lambda 1 is equal to 4 and lambda 2 is equal to 2. So the nice thing is these are two distinct eigenvalues, and we have a system with two equations in there. Therefore, when we solve for our eigenvectors, we can automatically say that they are linearly independent of each other. That's the cool part. All right, so it will have a full set of eigenvectors. All right, so let's find out what those eigenvectors are. So lambda 1 is equal to 4. So let's do this in blue. So when we plug 4 into our matrix of A minus I, or lambda I, we are going to get negative 3, 1, 1, multiplied by our vector x1, x2 is equal to the 0, 0. All right, so when we solve this, we are going to get negative 3x1 minus 3x2 is equal to 0. Or if we solve for that, we are going to get x1 is equal to, or negative x1 is equal to x2. All right, so that means for any x of I where we don't choose x to equal 0, we can form a non-trivial vector. So I'm going to say that I'm going to let x2 be equal to 1, so therefore x1 has to be equal to negative 1. So again, let x2 equal positive 1. All right, so lambda 2, which is equal to 2, and when we throw it into our matrix of A minus lambda I, we're going to get negative 1, negative 3, 1, 3, times x of 1, x of 2 is equal to 0, 0. All right, so negative 1, x1 minus 3, x2 is equal to 0. And notice that if we multiplied 1, 3 to x1, x2, we were going to just get the negative of, or the positive of this. So it's the same equation, just multiplied by a scalar constant of negative 1. So when I solve this, I'm going to get x1 is equal to negative 3x2. Therefore, for any value besides x is equal to 0, I can form a non-trivial solution. So if I let x2 equal 1, I can get negative 3 for x1. And that's how you find your eigenvectors. All right. Again, recall from our previous section that solutions are of the form y sub t is equal to e to the lambda t x. So our general solution and again, I want to make a note here. Note we have two distinct eigenvalues. Therefore, the eigenvectors are linearly independent. And the solutions form a fundamental set. Okay, so therefore, we can get into our general solution. All right, and our general solution is of the following form. Y sub t is equal to C1 e to the 4t times negative 1, 1 plus C2 e to the 2t times negative 3, 1, which if we wrote this out as a matrix, we would get negative e to the 4t, negative 3e to the 2t, e to the 4t, e to the 2t, times C1, C2. All right. Now it's time to solve. So we know y sub 0 is equal to 1, 1. Therefore, y sub 0, when I plug it into my general solution, all right, for every t, we're going to plug in a 0. So notice that we're going to get negative 1, negative 3, 1, 1. We're going to multiply that to our C1, C2, and set this equal to 1, 1. So now, all we have to do is set up an augmented matrix. Here's our solutions for our IVP, which is 1, 1. All right. And now we can just do a very simple row reductions, and we're going to get a very clean answer here in just a second. So I'm going to do row 2 plus row 1. When I get that, I'm going to get 0, negative 2, 2, negative 1, negative 3, 1. Let's go ahead and make this guy we're going to simplify where we're going to get negative 1 here, change it to a positive 1, and then change on row 2 the non-zero term into a positive 1 as well. So I'm going to do negative row 1, negative 1/2 row 2. So that leaves me 1, 3, 1, 0, 1, negative 1. All right. And then I'm going to get a 0 here where that 3 is. So I need to do row 1 minus 3, row 2. And that will leave me 1, 0, 2, 0, 1, negative 1. Which means C1 is equal to 2 and C2 is equal to negative 1. Therefore, thus, y of t is equal to negative e to the 4t, negative 3e to the 2t, e to the 4t, e to the 2t, times 2, negative 1. And that's all we have to do. And then if we multiply this out, this will give us our two solutions. So negative 2e to the 4t plus 3e to the 2t. And then this row times this column, we're going to get positive 2e to the 4t minus e to the 2t. And that's all we have to do. All right, so let's look at the next one. So that was a 2 by 2 solving for an IVP. So it wasn't horrible. It is very doable. Nothing too bad on that part. Again, solving for C1, C2, you set up an augmented matrix, and then you will get, once you do row reduction on the left-hand side, once you get that identity matrix, C1 is your top value, C2 is your second value. And notice, and that's because we have the diagonal 1, 1 here. If you had moved any rows around, you have to be careful where that 1 is placed. So C1 is the first column, C2 is the second column for that part. All right, so find the general solution of the following. So we have 2y1 minus y2 minus y3 minus y1 plus 2y2 minus y sub 3. And then our third differential equation is negative y sub 1 negative y sub 2 or minus y sub 2 plus 2y sub 3. So first of all, again, the best thing to do is go ahead and set up your matrix. So A is going to be of the form 2, negative 1, negative 1, negative 1, 2, negative 1, negative 1, negative 1, 2. All right. So this is what I mean by looking to see if, so before I go about solving for my eigenvalues, one thing I'm going to note here is that A is symmetric. All right. Therefore, A has a full set of eigenvalues or eigenvectors. Okay, that means once we solve for our eigenvalues, that means our eigenvectors will be linearly independent of each other, and they will form a fundamental set based upon our definitions from theorem 4.6. So this is very, very important. All right, and we're going to see why this is important here in just a second. So let's look at the determinant of A minus lambda I. So here we are going to get 2 minus lambda, negative 1, negative 1, negative 1, 2 minus lambda, negative 1, negative 1, negative 1, 2 minus lambda. All right. When calculating the determinant, we're going to deal with the minors again. So I'm going to circle these in different colors so that way you can see where they're coming from. So we're going to get 2 minus lambda times its minor of 2 minus lambda, the quantity squared, and then negative 1 times negative 1 times negative 1 is going to be positive 1, so minus 1. All right, in red, here's our second one, minus negative 1 times its minor of negative 1 times 2 minus lambda, minus negative 1 times negative 1, so that's going to be minus 1. And then lastly, in blue, we're going to deal with that one. So plus negative 1 times its minor of positive 1 plus 2 minus lambda. All right. So now we need to go into simplifying. So for this, move everything back to green. We're going to get 2 minus lambda times lambda squared minus 4 lambda plus 3 plus lambda minus 3 minus 3 minus lambda. All right. Now we're going to multiply this into there. We're going to get 2 lambda squared minus 8 lambda plus 6 minus lambda cubed plus 4 lambda squared minus 3 lambda. And then notice here that we're going to get plus 2 lambda minus 6. All right. Combining like terms and moving things around, we're going to get negative lambda cubed. So I like having my highest power out in front. All right. Look at the lambda squareds. We're going to get plus 6 lambda squared minus 9 lambda, and then everything else is going to cancel out. Well, the negative 6's are going to cancel out for that part. So we can factor this. We're going to get negative lambda, lambda minus 3, the quantity squared, and we're going to set this equal to 0. So lambda 1 is equal to 0, but lambda 2 and 3 are both equal to positive 3. So we have repeated eigenvalues. But wait one second, that's not what we were dealing with just without any repeats. Well, this was real eigenvalues is the name of this section. We are going to be dealing with repeats later on, but notice we do have something that helps us out here. Even though we do not have distinct real eigenvalues, we do have a symmetric matrix which then guarantees the existence of linearly independent eigenvectors for that, regardless of the eigenvalues. Okay, so the very first thing that we need to do is we still need to solve to find our first our eigenvalue, or sorry, eigenvector. All right, so lambda 1 is equal to 0. So when I plug that in into my a minus I lambda, I'm going to get 2, negative 1, negative 1, negative 1, 2, negative 1, negative 1, negative 1, 2. Multiply that by our x of 1, x of 2, x of 3, and set it equal to 0 for that part. So now we can do row reduction on this one. So when we do that, I'm going to set up an augmented matrix, even though the right hand side, since it's all zeros, we technically don't even have to incorporate that, but I'm just being mathematically, sorry, I've already started on that one. 2, negative 1, negative 1, negative 1, negative 1, 2. All right, so the first thing I'm going to do is I'm going to do row 1 plus row 2, and then row 3 minus row 2. All right, so that's going to give me 1, 1, negative 2, 0. Then I'm going to get negative 1, 2, negative 1, 0, because we didn't do anything to the second row. And then 0, negative 3, 3, 0. Next thing I'm going to do is get rid of this one here, so I'm going to do row 2 plus row 1. And then multiply by negative 1/3 row 3. All right, so I'm going to get 1, 1, negative 2, 0, 0, 3, negative 3, 0, 1, negative 1, 0, 0. One more set, 1/3 row 2, 1, 1, negative 2, 0, 0, 1, negative 1, 0, 0, 1, negative 1, 0. So notice if I do row 3 minus row 2, and I do row 1 minus row 2, I get 1, 0, negative 1, 0, 0, 1, negative 1, 0, and then a row of zeros on my last one, which means x3 can be any value for that part. Okay, so when we solve this, I get, again, in my row reduced form, I have positive 1, 0, negative 1, 0, 1, negative 1, 0, 0, 0 times x1, x2, x of 3. All right, so that means x1 minus x3 is equal to 0, and x2 minus x3 is equal to 0. So another way to state that is x1 is equal to x3, and x2 is equal to x3, and x3 can be any value not equal to 0. All right, so to get a non-trivial solution, we're going to let x of 3 equal 1. Therefore, our eigenvector x1 is equal to 1, 1, 1. All right, so there's our first eigenvector. Now we need to solve for our other two. Well, we have these repeats. So let's do this in red. To find the eigenvectors, corresponding to the repeated eigenvalues, lambda is equal to 3. We first solve a minus 3i. Okay, so we're still going to do that process, so nothing's going to change. Well, when I plug in positive 3 into our equation, or a minus I, or lambda I, we're going to get the following to happen. So we are going to get the system negative 1, negative 1, negative 1, times x1, x2, x3, and set it all equal to 0. Well, it doesn't matter which one we solve, we are going to get the same thing for every single time that we multiply the row times column. We're going to get negative x1 minus x2 minus x3 is equal to 0. Or another way to state that is x1 plus x2 plus x3 is equal to 0. So in the end, we look like the following matrix. Because again, by row reduction, we can just add or subtract row 1 from both rows, and this is what we'd get. So no surprise there when everything is repeated. All right. Meaning, we get the following. So this means x1 is equal to negative x2 minus x3. And x2 and x3 can be any value. All right. So if we look at the vector formed by that, we get negative x2 minus x3, x2, and x3. Well, if we rewrote this on what they could be, this means this could be x2 times negative 1, 1, 0, plus x3, negative 1, 0, 1, if we separated it out. Okay? So, if that's the case, I can just use these two vectors as my eigenvectors. So thus, two linearly independent eigenvectors corresponding to lambda is equal to 3 are x2 is equal to -1, 1, 0, and x3 is equal to -1, 0, 1. Thus, the general solution is the following. Y of t is equal to C1 times our first eigenvalue when lambda is equal to 0. So that means we're going to get e lambda t times x1. So e to the 0 is 1 plus c2 e to the 3t times its eigenvalue of eigenvector of -1, 1, 0 plus c3 e to the 3t times its eigenvector, which if we wrote this out, matrix form, we get 1 negative e to the 3t, negative e to the 3t, 1 e to the 3t, 0, 1, 0, e to the 3t, times the vector c1, c2, and c3. And that is the end of that problem. So this is the way if we don't have distinct but we have a symmetric matrix, this is the process to go through in order to find your linearly independent eigenvectors. And the nice thing is when you have the really cool thing about this is when you have a symmetric matrix, then you're guaranteed to have linearly independent eigenvectors. And a way that we can check that is to find the determinant of the 3 by 3 matrix using the 3 eigenvectors and show that it's not equal to 0. And that's all we'd have to do. And that would show that it's a fundamental set in that case. All right, so moving on. Let's look at what a phase plane is. So again, I said that we're going to be looking back at section 1.3 just as a kind of a methodology of what we're going to be looking at. So recall from section 1.3 that we can see how the solutions of scalar equations, so for us when we were looking at 1.3, those were just differential equations, we can see how they behave by graphing them in the ty plane. So we developed what we call direction fields, where we had those line segments, or sometimes called filaments, showing the slope field, if you will. So we're going to use a similar approach for linear systems of the form y prime is equal to ay. But for us, we're limited to just a 2 by 2 in this case. Y sub 1 prime is equal to a11 y1 plus a12 y2, and y2 prime is equal to a21 y1 plus a22 y2. And the reason that we're using these subscripts is just saying it's coming from the A matrix, where A has the following components: a11, a12, a21, and a22. So that's where those are coming from. All right. So again, constant matrix and all that fun stuff. So this graphing tool is known as the phase plane, and we're going to construct one here in just a second. All right, and I'm also going to give some helpful hints on how to graph these, because these filaments we can draw, but then they also have a direction to them as well, since we are dealing with vectors. So they have a direction for that part. So here we create the independent variable t. So this is a little bit different. So it's not as direct as we dealt with direction fields. So there is a little bit of a difference. There is a difference to these. So we're going to treat the independent variable t as a parameter. So remember parameterization from Calc 2. This is going to lead into on how to graph these guys, and then we're going to plot the solutions in the y1, y2 plane. So our if you will, our independent axis is now y1, and y2 is the dependent, if you will. So our horizontal axis is y1, our vertical axis is y2. So when we construct these, that's how it's going to look. All right. So to construct a phase plane plot for the system, we would typically have to find the general solution. So here, A would equal 3/5, 4/5, 4/5, negative 3/5, and then we'd solve. And so here I'm going to go ahead and give you the general form of it. By solving for the eigenvalues and eigenvectors, vectors or eigenpairs, we get the general solution as y of t. So you can practice this one on your own if you will. E to the t times 2, 1 plus c2 e to the negative t times 1, negative 2. And so what we could do then is plug in varying values of c1 and c2 and graph the solutions that way. So we could study its behavior that way. That would take quite some time, but we could do it. However, one really cool aspect of the phase plane is that we can obtain a qualitative information without actually having to solve the system at all. So from calculus, we know that the slope of the line tangent to the solution curve of a system passing through any point is given by the following. So I went ahead and typed this one up because my handwriting looks horrible, so I won't torture you as much. So what it is the derivative of the second solution divided by the derivative of the first solution. And so what it is we already have those. We're given what y1 prime is and what y2 prime is. So in our case, y2 prime was 4/5 y1 minus 3/5 y2. And when we solve, and then y1 prime is 3/5 y1 plus 4/5 y2, and then multiplying all the way through by 5 or canceling out that, we get 4y1 minus 3y2 divided by 3y1 plus 4y1. So this means we have the solution at any given point y1, y2. So that's the cool part. So for any point y1, y2, we can find the slope of the curve at any given point. So by using small filaments or line segments with slopes equal to those values, we can generate what we call the phase plane direction field. And sometimes this is referred to as a vector field, which is why we are going to have arrows here in a second. So what we need to do in order to help with graphing these vector fields, there are some helpful observations, is the directions of each of these line segments that we're going to be generating is all dependent on the value in the numerator versus the value in the denominator. So first of all, if y2 prime is greater than 0 and y1 prime is greater than 0, so that means the numerator is positive and the denominator is positive, then the arrow is going upward to the right, meaning it's going to look like, and I'm going to do these in blue, our filaments are going to look like that. Number 2, if the numerator is positive, but the denominator is negative, again, remember y2 is up on top and y1 prime is on the bottom, then the arrow is going upward. To the left. And so when you draw that arrow, it's going up and to the left, but notice what the slope is. The slope of just the line segment itself is negative. Okay, so we still are maintaining that value. All right. If y2 prime is negative, so if the numerator is negative, but the denominator is positive, then the arrow is going downward to the right. All right, so notice that the line segment still has a negative slope, but we're going down and to the right this time. And lastly, if y2 prime is negative and y1 prime is negative, the arrow is going downward to the left. So notice that the line segment still has a positive slope, but the arrow is pointing down to the left. All right. Well, there are going to be times where we get zeros. So this is dealing with horizontal arrows. So when that occurs is when our y sub 2 prime is equal to 0. So that's when we have our numerator is 0. So if y1 prime is greater than 0, the arrow goes to the right. All right. So I know what you guys know what that looks like. So there you go. So notice that the line segment has a 0 slope. And if y prime is negative, y1 prime is negative, the arrow goes left. All right. And then vertical lines is when the denominator, so y1 prime is equal to 0. This is when you'll deal with vertical lines. All right. So if y2 prime, the numerator, is positive, the arrow goes upward. So notice that it has an indeterminate slope. And if y2 prime is negative, the arrow goes down. All right. So to kind of illustrate this, I'm only going to do a few of these and then show you what these graphs will look like. And I used the I forgot the name of the website, but it's down at the bottom of each of the pictures that I graphed. And so I'll say it when we get down there. So I'm not going to butcher the name right before I show you how to spell it. So it's the same one that I showed you. It's by the same group that I showed you how to build direction fields. So it's a nice free website to use that for. You just got to be careful. Your y1 prime is your x function. Your y2 prime is your y function. So that's the only difference. So instead of having y1, y2, they have x and y. All right, so that's the biggest thing is when you're graphing them, that's how you go approach those. So for our example, we had dy sub 2 dy so 1, is equal to 4y1 minus 3y2 divided by 3y1 plus 4y2. So I'm just going to look and graph a few of these. So I'm not going to graph all of these. So I'm only going to look at a 2 by 2 square. So I'm going to plug in a couple of values and we'll see how we find these guys. So I'll try to throw some negative ones in there so then that way you can see how these guys are looking. All right. So y1, y2. If I deal with the point 1, 1, and 0, 1, we'll do one more. We'll deal with negative 1, negative 2. All right. When I look at dy y1, when I plug in 1, 1, I'm going to get 4 minus 3 over 3 plus 4. So I'm going to get 1/7. All right. Notice that the numerator and the denominator are both positive. So that means it's going to go up and to the right. So at the point 1, 1, we have a slope of 1/7. So I'm going to try to exaggerate this as much as possible so that way you can see. So our line filament would look like something like that. All right. At 0, 1, we get negative 3 over 4. Notice I'm keeping my negative up at the top instead of bringing it out front, and that's to show me which one's negative, which one's positive. So here I have negative top, positive bottom. So that means it's going to be going down and to the right at 0, 1. So at 0, 1, this is what the line segment looks like. And then at negative 1, negative 2, we're going to get negative 4 plus 6 divided by negative 3 minus 8. So notice that we're going to get a positive 2 and a negative 11 on the bottom. So at negative 1, negative 2, so that's going to be down here. All right, so the numerator is positive, but the denominator is negative. So our arrow is going to be, and that's too much of a slope. This is a little bit flatter. So we're going to get an up and to the left is how it's going to look. All right, so that's how you would start plotting these on a 2 by 2 frame. So I wouldn't do much of these to you, but that's the nice thing is I could give you any 2 by 2 matrix, and you guys can calculate the direction field or be able to identify a phase plane, be able to find that phase plane based upon its matrix. So if we were to graph this on a 2 by 2, and so I'm going to show you what this looks like. So this is what a filled in 2 by 2 grid would look like if we started graphing all these points. Now the only thing is, notice here with the numerical step and integration length, this is dealing with the actual solutions, so you don't worry about the parameters. It's the equations that you want to look at. So you can't change much like what we did with direction fields, but notice here, this is your y1, this is your y2. and this is your y1 and your y2. All right. So if we were to plot a point on here based upon the directions, see, notice that these guys, this -1, -2, is going up and to the left. So that means our graph would look something, and I'm going to do a horrible representation here, something of that form. Okay, so the next plot I'm going to show you is going to give you an idea of what these guys look like. And in fact, it's really cool. So GeoGebra is how they pronounce it, I'm assuming. But if you click on that link, you'll be able to go there and graph these guys yourself, so you can play around with different ones. So if we were to look at specific solutions, notice that they have an arrow indicating the direction of travel for that, and that's because now we have these different directions that we're going to be going in this vector field. So this is what I wanted to show you. So that's the cool thing about this, is you can graphically see how these things are operating just like direction fields without having to solve them. So in the next section, 4.6, we'll get into complex, and then we'll get into repeated. Have a good day.